So to rewrite that in exponential form, you're looking at, typically, what's the base, what's the exponent, and what does the thing equal when it's all done? You could think of it like here to there, however you want to look at it. My base is 8.5. What a logarithm equals is the exponent, 614.125. Now that doesn't help you in any way solve for a, not at all. But that's just converting from exponential to logarithmic and being in the habit of being able to do that quickly and easily. Because if I wanted to find the value of a, which this question doesn't originally ask, but we should do that anyways. How do we find a when I have logs of uncommon bases? Well, I would use the change of base formula, which you probably don't remember, or if you do, then congratulations, you're a step ahead of most of us. But the change of base is this. If I have log base b of some number a, that will equal standard log of a over standard log of b, or natural log of a over natural log of b. Or, I mean, honestly, you could have any base you want, but your calculator typically only comes with natural log and log base 10. So for most of us, we would grab this in our calculator, and I would do, all right, natural log of 614.125 divided by the natural log of 8.5. And that would be what the value of a is. So if you have these uncommon bases, that's how you get it. Or vice versa. If you're working in something and you convert from exponential into logarithmic, and you result in having uncommon bases, this is how you could then work your way through it to find the actual answer. Now, I'm not going to do that right now because you have calculators, setting it up, plug the numbers in. Don't forget, though, when you're doing these on some calculators that you put your end parenthesis in, because if you do natural log of this, and then you go divided by natural log of that, it'll actually have the natural log of 8.5 inside of this parenthesis set, which makes it a completely different answer. All right, so then, more realistically, solve for x. There should be like a little colon right there so that we don't think that the at x is part of solve for x, colon, that equation. Get in the habit of set it up first. So go ahead and set it up. Which is my base? 1/4. What is my exponent? 3/2. What does it equal? X. Now it's a matter of, do you remember what fractional exponents are? Or how you use fractional exponents? A couple different ways you can go. I would go like this. 1/4 to the 1/2 to the 1/3. I'm splitting it way apart because when I have exponents, powers raised to powers, they multiply. So in this case, I pulled those apart. 1/2 times 3 is 3/2 because I know that the 1/2 means the square root of 1/4 cubed. Which I then go, okay, square root of 1 over the square root of 4 cubed. And the square root of 1 is 1. Square root of 4 is 2 cubed, or 1/8. Now you could do it the other way around and take the cubit first. 1 over 4 cubed. 1 cubed is 1. 4 cubed is 64. And then the 1/2 power is square root. So I'd have 1 over 64 square rooted, which would be 1 over 8. Ta-da! Solving logarithms. Back to these. Domain, range, asymptotes, end behaviors, other values that I can do with and not do with, and those kind of things. So for some of this, especially with logarithms, is remembering, well, what does a logarithmic curve look like? What can I do? What can I not do? If you can't remember that because you're like, and I'm typically myself, not a person who says just memorize it. Try to think through logically what's happening. 5 to some power equals this stuff. Or if I move that 7 over, it would be f of x minus 7 equals log. Now, you don't have to do this, but in my head, this is what I'm thinking through when I'm trying to determine what things can be and cannot be. 5 to some power will equal this value. Okay? If I take 5 to a power, any power, what can that never be? It can never be 0. So 5 to some power can never be 0, which means that 39 minus 13x cannot be 0. Is there anything else that it cannot be? 5 to a power. 5 to any power, whether it be positive, negative, fractional, 5 to the 0 power is 1. But 5 to any power is always positive. So not only is it not 0, it must be greater than 0. So, negative 13x greater than negative 39, divide by negative 13. Jogging our memories back to those algebra skills that when I divide by a negative number, the direction of my inequality changes. Because if I change the sign, and I change that sign, then I got to change the sign. Now, the other way around it, I could have taken this, added it to both sides, move that 13x over, and then 39 is greater than 13x. Divide by 13, I have 3 greater than x, which is the same as x less than 3. So I have a restriction on my domain. My domain is x less than 3. So it cannot have a number larger than 3. And if you want to, you can throw it in there and check and do a number like 10, or I don't care what number. You're going to get a negative, and try to do a log of a negative number in your calculator. It's not going to like you. Like a lot. It'll say error, dome mismatch for domain mismatch if you have a graphing calculator or something like that. All right, so I have a restriction on my domain, which probably means I have an asymptote. What can x not equal? 3. Because if it is 3, 39 minus 39 is 0. 5 to what power is 0? Not possible. So I'm going to have an asymptote at x equals 3 as well. Is there anything else that we cannot have? Is there anything else that I cannot use for range? All right, I'm going to have f of x minus 7. And here's where then if you recall what graphs look like, so I'm going to be looking at it like this. Here I am at 3. 1, 2, 3. Going to have this asymptote running here. And I can only be less than 3. So I don't know why I drew my graph way over here. It's going to go that way. All right. If I put in 0 for x, 0, 39 minus 0 is 39. Then I'm going to have some weird number, log of 39 over log of 5. Can find that number, then add 7 to it. It's going to be some type of a value up here. Don't know where it is. Could calculate it if I wanted to, but there's my y-intercept. All right. Can this function... Can all of this be negative? Can I drop below the x-axis? So then you're trying to figure out, well, what's going to go on as I do this? All right, but I'll go with this, start with. Let's talk about end behavior. Oh, we'll go back to that, sorry. We'll say, what is this? Is this equal 0? We can solve for x. I'm going to go up as I work through this. So then log base 5 of 39 minus 13x equals negative 7. right? Subtracted the 7. Convert that into exponential form. Now I'm going to move it down here. 5 to the negative 7th is equal to 39 minus 13x. 5 to the negative 7th is going to just be a really small number. 1 over 5 to the 7th. Minus 39 equals negative 13x. Divide by negative 13. X will equal all of this divided by negative 13. This number here is negative. This is almost 0 minus 39. That's negative. But I'm dividing by negative 13. That'll be positive. So it will cross the x-axis somewhere here. Let's see. It'll be just under 3. How do I know it's just under 3? Well, this is just over 39, or just under 39, sorry. Just slightly less than 39 divided by 13. So 39 divided by 13 is 3, so just less than 39 divided by 13 is just less than 3, which means my graph will be something like this. Shoot. Shoot. As I'm getting into some... Come on, shrink. There we go. The limit as x approaches 3 from the left. I'm getting into some things that we're going to cover the next class period. As I approach 3 from the left, coming this way on x, x approaches 3 from the left. That's what that means. My graph is approaching negative infinity. The limit as x approaches negative infinity, so now as x goes out here forever and ever and ever and ever, my graph is going up of f of x equals positive infinity. And again, if you can't remember that, you can always just take a really large number. And it doesn't have to be log base 5. It can be log of anything, because eventually they're all going to have similar qualities. Take a log of 100,000, take a log of 1,000,000. That number gets bigger. Not very fast, but it gets bigger. And then you add 7 to it, so whatever. It's just going to go up 7 more from whatever that large number is. So I have a domain restriction. I have asymptotes. Once I figure out this, I realize that my range has no restrictions. And there are no values that my y cannot be, so I do not have any horizontal asymptotes in logarithmic functions.
Is that negative?
So yes, the power is on the e. Negative 5 times e to that power, minus 4 equals 64. So when in doubt, just start with something. Got to solve for x, got to get rid of all the things that aren't x. Equals, 68, because I add 4. Oh, I somehow forgot to write my x and my exponent up there. It's negative 4x minus 1. Divide by negative 5. Which can't be reduced. I'll just leave it like that. And then we have to remember, how do we solve for variables in the exponents? Well, if I can convert this and rewrite my exponent as a logarithm, that might help. What is my base? My base is e, so it's going to be natural log. In a log equation, where was the exponent? It was on the other side of the equal sign. So it'd be the natural log of negative 68/5. So then take out your handy dandy calculator. Find e to what power is negative 68/5. What does your calculator tell you? Domain error. Your calculator tells you that because this side of the equation is asking e to what power is negative. E to any power, whether it's a positive or negative number, will always be a positive number itself. You take any number, any positive number to a power, it will always be a positive number. Which means this has no solution. So then here, and I'm going to change this to plus. That'll make life a little bit easier for us. So now the question is, will this have an answer? Do you notice the difference in the two equations? Start with the same idea. 5e to the negative 4x plus 1 equals 60. That'll be a little bit easier to work with because I changed it to plus 4. Divide by 5. E to the negative 4x plus 1 equals 12. Remember back when you were in elementary school and you were asking, the smart alecks in the class were asking their teacher, not any of you, of course, multiplication tables, when are we going to ever use this? The answer is only every day of your life when you have to multiply things. But if you remember them, it goes a lot faster. Then do the same thing. Take the natural log of both sides. When I take the natural log of both sides, is what you get, because natural log and e are inverse functions. Or you think, like we did on the previous slide, e is my power, or e is my base, so I take natural log of, and the exponent is negative 4x plus 1, of the 12. So either way of thinking about it, I'll be in the habit of starting to do this more, where, oh, I've got natural log, I have e to some power, natural log of e of something, they are inverse functions, leaves me just with the exponent. And then I take natural log of the other side, because whatever you do to one side of the equation, you always do to the other side of the equation. Negative 4x equals negative 1 plus the natural log of 12, which will be just a number. I just haven't written it yet. X equals negative 1 plus natural log of 12 all over negative 4. And at that point, you just have a number value, calculate your numerator, hit enter, or equals, or whatever you do, then divide by negative 4, so you don't accidentally have that negative 4 only under your natural log of 12. And you'll find out what that number is, which is just a matter of you using your calculator correctly. And as was just pointed out after completing this entire slide, that I managed to totally change the problem by making that a plus 1 there. I just transposed it wrong. But if you did this and worked it out the wrong problem the right way, I've been told by someone in the room that this is the answer if you plug it into your calculator. So obviously that wouldn't be the answer to this question, but this is another prime example of if you transpose things wrong and work it out correctly, you're still going to get a 4 on this problem on any exam because you've demonstrated full understanding of the concepts of what this problem is trying to assess. You made a mistake of just transposition, which I have no problem with. It means also that I have to go back and rework the entire problem the way you did it, as opposed to the way everybody else did it. But that doesn't bother me one iota. So if you followed this and did it the way I did it the wrong way, you should have had as an answer negative 0.37122. If you did it the right way, with the negative 1 here all the way down, which would then make this a positive 1, then that's your final answer. All right. So now we're going to take a problem and expand it out a bit in terms of exponential form. So exponential form, this one, generically speaking, f of x equals a times b to the x. There's just the most basic way of writing an exponential function. Within that, then we've done problems like this one where we talk about the amount that you have after a certain amount of time is equal to the principal times 1 plus r over n, where n is how many times you're working with your function. If it's a finance function, how many times a year, or how many times per whatever period you're talking about, to the nt. It's still the same equation. A is p, b is this number in here, and then x is how often you're going to be compounding things. But in the question that we have here, it asks us, find the difference in time required for initial investment of $1,000 to triple if your two options, so we're going to do this problem twice, are a 6.5% evaluated quarterly and a 6.25% evaluated continuously. Well, continuously, that's a different equation. When you're evaluating something continuously, it's f of x equals a times e to the rt. And we can make that a p if that makes you feel better. P times e to the rt. P is principal, f of x, or in this case, a of t, is equal to. So if I start with the quarterly, I would start and say a equals p times 1 plus r over n to the nt, plug in some numbers. If it triples, that'll be 3,000, because we can do that in our heads. 1,000, 1 plus 0.065 over 4, because it's going to be compounded quarterly, to the 4t. Three equals 0.065 divided by 4 is, so 1 plus that would be 1.01625 to the 4t power. Powers are in my exponents. Time to do some logs. Log of 3 equals log of 1.01625 to the 4t. Properties of logarithms. This can maneuver down in front. So I'll have that whole thing times 4t, which means 4t equals the log of 3 divided by the log of 1.01625. And then finally, I would divide by 4. So I can do that in my calculator, find out that t equals, so doing that, 17.04 years is how long it would take to triple if you're doing a 6.5% quarterly evaluated investment. Procedure similar, but now for continuously. 3,000 equals 1,000 e to the rt. So 3 equals e to the 0.0625 t, because different rate. So natural log of both sides, natural log of 3 equals 0.0625 t. You'll notice I didn't write the natural log of that side because they're inverse functions. Natural log of e are inverse functions. To use language that I don't like saying ever out loud is they cancel. They don't actually cancel. They're inverse functions. But they eliminate one another, leaving me with just the 0.065 t. So then I take the natural log of 3, which on my calculator is 1.098612289. Divide that by 0.0625. T equals 17.578 years. But then the question asked, find the difference in time required. So at a lower interest rate, just take the subtract them there, a little over half a year. A little bit over a half a year difference. Now granted, they're two different interest rates. If you did them as the same interest rate, you would find that the amount of time it takes to triple isn't that much time. It's less than a year. It's actually probably less than a month in difference. But the compounding continuously does get there slightly faster. So a question like this is assessing use of logarithms, use of exponents, use of the formula. In this case, you were not expected to calculate the initial value or things like that, like the ones we did on the first exam. But it's that similar concept, similar idea. All right, moving right along. More with exponents, making it a little bit more challenging now, or at least it looks like it is. Population of wildlife habitat is modeled by that equation, where T is in years. How many animals were originally transported to the habitat? So here you were not given the initial amount. You're asked to find the initial amount. Well, if we're measuring it in T in years, when will the initial amount be? When T is 0, because that's when things started. So to find the initial amount, take this and we're going to find P of 0. P of 0 is equal to 360 over 1 plus 6.2 times e to the 0. Right. Negative 0.35 times 0 is 0, so e to the 0, but we know e to the 0 is 1. Anything to the 0 power is 1. 360 over 1 plus 6.2, which is 360 over 7.2, which is 50. So my initial amount was 50 animals. It says how many animals were originally transported to the habitat? 50 critters. All right. And then the question says, how many years will it take before the habitat reaches half its capacity? So now I want my final product, my end amount, to be 25 equals 360 over 1 plus 6.2 e to the negative 0.35 t. Need to solve for t. (25) times 1 plus 6.2 e to the negative 0.35 t equals 360. Just doing some algebra there. Divide by 25. $14.4. (6.2 e to the negative 0.35 t equals 13.4. Subtracted the 1. Divide by 6.2. E to the negative 0.35 t equals 2.16129. Take the natural log of both sides. negative 0.35t equals whatever that number is. And then divide that by negative 0.35. So when will it be half the amount? 2.2 years ago. So whenever they're talking about starting, will all depend on what they're starting to and from. And you might say, well, I found an answer. My answer doesn't make sense. Could mean I did something wrong. Could mean my answer doesn't make sense in the context of the question as well. Could mean that their model is bad. But in terms of interpreting the answer, it'd be 2.2 years ago. As far as exponents and logarithms go, anything else, a lot of times is just remembering a lot of the properties of it, remembering how they work together, remembering things like a to the x times a to the y is a to the x plus y, similar to log of x plus log of y is equal to log of xy. There's a reason why that all makes sense, is because logarithms and exponents are the same thing, just written a different way. One of them is multiplying to get to adding, the other one's adding to get multiplying, but they're connected when you're talking logarithms and exponents. As far as the exam goes, it's working at, I want to ballpark it and say I think I've got about 12 or 13 questions right now for the 2 hours, and they're all just, I think they're all just one question per problem. So it's not like one problem in like ABC. I take that back. I know there's one that's like multiple steps on there, but it's building off of one idea to the next, to the next, to the next. And while I'm on that topic, if you get to a question on an exam, and I would say this would hold true not just for me, but I would carry this over and possibly in future classes you have with other instructors of various types. If you have a multi-stage question and you can't do part A and part B builds off of part A, make up a reasonable idea of what part A maybe could have been, and then do the problem from your made-up answer. Because then you will be demonstrating, well, I can't get there, but I'm pretty sure I know the next thing you're supposed to do with that is da-da-da-da-da-da. It's demonstrating to the instructor that, hey, okay, crud, like, I can't remember that, but I know this next thing is supposed to be this, or supposed to be this. Or you get to a solution that you know doesn't make sense, articulating why you know it doesn't make sense. Like, I got -2 years. I don't know if I did something wrong. And if that previous slide were a question on an exam you're doing for me, my recommendation is if you see it and you're like, oh no, go on. If you're like, but you are showing a lot of steps and you're doing good, like correct math processes, come back to that at the end if you have time. Go on to the next one. Because if you take too much time nitpicking your way through, and this is for me, nitpicking your way through to find a missing negative or a missing number, but procedurally it was all there, you're going to get full credit anyways. It's not going to behoove you to spend that much time going back to find it. If you're just uncomfortable seeing that negative and it just like personally attacks your math nature, then yeah, go back and do that. But don't do that when you have more to do on the exam, spending your time wisely to use that time to. Other strategies that I say on the instructions are always read through the exam, take a quick look, and if you know there's something that you're like, oh, I got that down so quick and easy, start there. Start with the problems that you know you're going to be able to hit on all cylinders on, and use that there.